Okay, hello everyone. I'm going to be recording a series of videos on artificial intelligence. This is a bit of an experiment. A friend of mine recently asked me if I could explain AI in simple terms. And so I figured I'll create some videos to do that. Of course, there are many uh, videos out there. There's a lot of content out there on AI. AI is a very hot topic. It's in the news these days. It's everywhere. We use it all the time. So I certainly won't pretend to kind of, add anything original to these videos. My goal is to maybe give some idea of what AI is by focusing on certain topics that are of interest to me, and in the process, hopefully also make it somewhat entertaining and interesting. So let me start by sharing my screen. Okay, so introduction to AI, part one. So I'm going to start with the question, what is AI, right? And to answer the question, what is AI, we can ask the question, what is intelligence? What does an intelligent entity do? What are those specific qualities that an entity must have before you call it intelligent, right? Here are some definitions of AI, and in particular, definitions of intelligence. So Noel and Simon, who were early pioneers in artificial intelligence, they have this definition. By general intelligent action, we wish to indicate the same scope of intelligence as we see in human action. So they're clearly comparing it to human behavior, which might be a little bit suspect because humans are not known to always exhibit intelligent behavior. But in any case, that's the definition that they're going with. But in particular, they're saying that in any real situation, behavior appropriate to the ends of the system and adaptive to the demands of the environment can occur. So they're qualifying that when we see intelligence in human action, what you're really seeing is behavior that is goal-oriented, right? And that is goal-oriented and at the same time adaptive to the demands of the environment. So they're saying that that in any real situation, behavior appropriate to the ends of the system and adapted to the demands of the environment can occur within some limits of speed and complexity. Okay, so that is a very general definition focusing on aspects of human behavior that are goal-oriented and adaptive to the demands of the environment. On the other hand, Marvin Minsky, also a famous computer scientist and also a pioneer in artificial intelligence, has a much simpler definition where he defines intelligence as the ability to solve hard problems. That's it. Okay, so I guess, by that definition, problems, of course, hard problems can be of all kinds. They could be mathematical problems. They could be, problems involved in playing a game. They could be all kinds. So I suppose it is a useful definition. If you have a system that's able to solve hard problems, we would think of that as intelligent. And then John McCarthy, also an AI pioneer, defines it as AI is concerned with methods of achieving goals. Of course, there's very explicit in saying it's about achieving goals in situations in which the information available has a certain complex character. The methods that have to be used are related to the problem presented by the situation. Again, there's an element of problem solving involved, and are similar whether the problem solver is human, a Martian, or a computer program. So here, I think he's sort of highlighting a certain universality to intelligence, where he's basically saying that um, to solve to exhibit intelligence, in particular for artificial intelligence, the methods that are used to solve the problem should be the same, regardless of the entity that is solving the problem, whether it is a human or an alien or a computer program, right? So there's a certain element of universality to it. Okay. Before we go deeper into definitions of AI, let's just look at the 20th century origins of AI. Of course, people have been thinking about AI and about intelligence and whether machines can think. Even before the 20th century, there have been philosophers who've been trying to understand, the human mind and logic, and the laws of logic were defined by George Boole. And then, of course, the history of artificial intelligence is intimately tied to the history of computing. Charles Babbage in the 1800s built his famous analytical engine, which was able to perform, complicated calculations. But really, I think the topic of AI really takes off with the advent of digital computers in the 20th century, and the work of several computer scientists and cognitive psychologists, neurophysiologists. So in the 40s and 50s is when this really took off, right? So let's start there for the purposes of our discussion. In the 1940s and 50s, between 1940 and 1950, there were two key developments. In 1943, McCulloch and Pitts published the Boolean circuit model of the brain. They introduced this concept of an artificial neural network. So they were basically trying to come up with a mathematical model for understanding the brain. This was very influential. Artificial neural network, was definitely a very influential concept, and it was later on it was picked up by computer scientists, and who used it to actually build the so-called perceptron. Another very influential paper was by Alan Turing, called Computing Machinery and Intelligence, where he proposed his famous Turing Test. And the Turing Test is meant to be a behavioral test for intelligence. He was trying to provide an operational definition of intelligence, and so we will talk more about this particular test, Turing Test. In the 50s, there were several developments. In 1956, in Dartmouth, there was a meeting of several computer scientists. There was a project proposal for spending a summer, or 2 months in summer, focused on solving or discussing several key problems in computer science, and in particular in artificial intelligence. The term artificial intelligence was first adopted at this conference in Dartmouth. In that same conference, there were two gentlemen, Newell and Simon, who came with a software program called Logic Theorist. And Logic Theorist was a program that could prove theorems in logic. In particular, it was able to prove several theorems from this famous book by Russell and Whitehead, Principia Mathematica. And Principia Mathematica is a famous book. It was written with the goal of laying logical foundations for mathematics, because prior to that, mathematics was considered to be not logically sound. Like there were too many assumptions in it. And although Russell and Whitehead didn't quite achieve their goal, because Gödel and Alan Turing introduced this concept of undecidability, which undermined the overall goal of providing a logical foundation for all of mathematics. However, Russell and Whitehead's book is still, is a very significant achievement, and it's a massive tome, very dry. Probably very few people in the world have read it, but Herbert Simon, had actually read the book, and he and Newell, came up with the idea of building a machine that could actually prove theorems in it. And they actually did achieve that to a large extent. And in that paper, they introduced some key techniques that are now part of classical artificial intelligence. They're still taught in courses on artificial intelligence. They're foundational, topics, in particular techniques like search trees and heuristics, using heuristics. These are all things that were introduced in their paper on Logic Theorist. Unfortunately, when Newell and Simon attended this meeting, their proposals were met with skepticism, partly because the group was very influenced by the ideas of McCulloch and Pitts around neural networks, the models of the brain, and people believed that you needed analog computers to achieve intelligence. Also, Turing's paper, of course, was also very influential there, whereas Newell and Simon were approaching the problem from the point of view of more of, say, computer science, of using algorithms and logic. And so around the same time, 1957, Rosenblatt took the ideas from McCulloch and Pitts on artificial neural networks and created something called a perceptron, sort of a software representation of the artificial neural network, and even simulated it on an IBM computer. And that was actually, he published a book on that as well. And that created quite a stir. It made the news. People finally believed that they had thinking machines that could solve any problem. And there was a lot of hype and a lot of expectation. And I mean, that could be one of the reasons, why, Newell and Simon's Logic Theorist was maybe not accepted, or was met with skepticism. So along the lines of Newell and Simon's work, in 1959, there were two additional developments. Samuels created a checkers program and wrote a paper about it. So checkers program, it could play the game of checkers. Game playing has always been a very essential aspect of artificial intelligence. And this was probably the first example of that. I mean, after that, you had, chess playing, Go playing, and a variety of other games. But Samuel introduced some of the very key ideas that you find that are used today in artificial intelligence and game playing, especially when you have adversarial search problems. And those ideas, and as well as ideas around heuristics, again, are found in Samuel's paper. Samuel, in fact, titled his paper Machine Learning. So the idea of learning by playing a game is something that is highlighted in Samuel's paper. In fact, let's maybe take a quick look at that paper, Samuel's checkers program. So here's the title of the paper. The title of the paper is Some Studies in Machine Learning Using the Game of Checkers. So really, Arthur Samuel was trying to use the game of checkers to illustrate machine learning. And this is 1959, well before machine learning had really taken off. And this is where a lot of these techniques of reinforcement learning, some of those ideas were already present in this paper. Another paper that came out was this geometry theorem proving machine by Gelenter, and this is a paper, and it was also simulated on a computer. There was a software program that was written, and its goal was to prove theorems in geometry. So solving mathematical problems, specifically proving theorems, this is the kind of the first instance of that. Logic theories obviously prove theorems in logic, but this is proving theorems in geometry, in mathematics. In particular, theorems from Euclid's Elements, and they demonstrated the ability to solve or prove many problems in geometry. Some of which were considered too hard for a high school student to prove. The computer was able to prove. Again, a lot of ideas from reinforcement learning, learning from by using heuristics, learning from experience. All those elements are there in this paper. And then in 1969, of course, so there were these two styles of doing AI, if you will. One was focused on logic, on problem solving, and sort of learning, and the other one was basically modeled after the functioning of the brain, of the neurons, and the perceptron. Certainly the perceptron approach probably was more popular until 1969, when Marvin Minsky published his book on perceptrons, where he highlighted some of the capabilities of perceptrons, but more importantly, he also highlighted the limitations of perceptrons. He demonstrated that the perceptron by itself could not solve certain problems. In particular, there's something called the XOR problem, which we'll talk about later on when we look at deep learning. It was perceived as an attack on Rosenblatt's work. And it really was a big disappointment for a lot of people who had very high expectations from perceptrons. And it sort of led to the AI winter of the 1970s. So, after that, it's not that AI, had completely, had stopped in its tracks. I mean, AI research continued after the 70s, even though there was a sort of a period of lull where, there wasn't that much funding for AI because of this, arguably because of this book by Marvin Minsky. But there were other developments. There were these knowledge-based approaches. There's something called expert systems, which are all, focused on encapsulating knowledge of the world and having rules, rules-based systems. Then there were probabilistic approaches as well. So, using statistical mechanisms, statistical learning. Neural networks were continued to be researched, but they hadn't taken off. But it was sort of by the end of the 20th century, I think the time was ripe for deep learning to take off, but that didn't happen until the 21st century. Let's briefly talk about the Turing test because it's so famous. There's this thing called the imitation game. There's even a movie by that name. It's a biography of Alan Turing. So it's quite a famous test. And the goal behind the Turing test that was proposed by Alan Turing was to provide an operational definition of intelligence. So basically, Alan Turing was trying to he sort of posed a question, or he was trying to determine what does it mean to have a thinking machine? Like, what is a thinking machine? How can you tell if a machine is able to think? And he posed this question because a very natural question that philosophers have been asking that question probably for ages. But what was different here was Alan Turing tried to make it very precise. He immediately realized that if you're going to ask the question, what is a thinking machine, you have to define what is a machine here, like what do you mean by a machine, and you have to define what do you mean by thinking, like what is thinking here, right? And he saw that there is sort of an inherent problem in this. When you talk about machines, you're talking about a very broad spectrum of entities, and when you're talking about thinking, it's really hard to define what is happening inside a human's brain when the human is thinking. This was before we had things like fMRI and other types of neurophysical tests. So what Alan Turing came up with was the idea that let's come up with an operational definition of intelligence. And let's also precisely define what kind of a machine we're talking about. This was, of course, when digital computers had started coming about, and Alan Turing had also published a famous paper on what's called computable numbers, where he talks about something called the Turing machine. And this Turing machine is meant to be a universal model of a machine, of a calculating machine. So any digital computer can be modeled by the Turing machine. And if a problem can be solved by the Turing machine, then that means it can be solved by any digital computer, right? So he chose a digital computer as his definition of a machine, and his goal was to provide an operational definition of intelligence for such a machine, right? And the operational definition that he gave was based on this test that involves a human investigator or an interrogator, if you will, who would pose a series of questions in natural language, and it would not be passed via voice, but it would be through text, right? It would be passed through text. And the questions are to be answered. Actually, I think this is meant to say it is not to be passed via voice. It is to be passed via keyboard. Okay, sorry for that error. So you don't want to use voice. You don't want to use anything that could indicate whether there's a human or a machine involved. So this is text that is being transmitted, and it is to be answered by a person or a machine that is invisible to the interrogators. The interrogator doesn't know whether it's a person answering or a machine that is answering. And the machine is considered to pass the Turing test if the investigator cannot distinguish between them, right? Meaning that they cannot distinguish between a human response and a machine response, right? And a machine is determined to have AI, artificial intelligence, if it passes this test, right? So here's a cartoon that shows you have a human interrogator who's sitting in front of a keyboard. They're posing a series of questions, and then you have on the other side a human and a machine, and they respond to these questions. And if the human cannot tell the difference, that means that system has passed the Turing test. And in this paper, he carries out, he gives a lot of examples of the kinds of questions that might be asked and the types of answers that the machine could give that would be indicative of intelligence. And, it suggested sort of major components of AI. These included things like having knowledge, being able to reason, being able to understand natural language, and being able to learn. So all those ideas were present in this seminal paper by Alan Turing. Okay, and here's a sort of the Dartmouth proposal. So this is the proposal that was made in August 31st, 1955, by this group of computer scientists, all very famous: McCarthy, Minsky, Rochester, and Shannon. Shannon, as in Claude Shannon, the inventor of information theory. So the proposal is, the title of the proposal is Proposal for the Dartmouth Summer Research Project on Artificial Intelligence. This is the first time these words, artificial intelligence, or this name, artificial intelligence, is used, right? And they say, we propose a 2-month, 10-man study of artificial intelligence be carried out during the summer of 1956 at Dartmouth College. The study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that a machine can be made to simulate it, right? An attempt will be made to find how to make machines use language, form abstractions and concepts, solve kinds of problems now reserved for humans, and improve themselves, right? And then they list out, various aspects of artificial intelligence problems that they propose to study, right? And so this is that famous summer project conference where these folks were present, as well as Noel and Simons, and this was a kind of a landmark event. You could almost say that this was, the birth of AI, if you will. Okay, so now, of course, through the 60s and 70s, while people were thinking about AI and there was research going on in artificial intelligence, AI as an idea had very much captured human imagination, and possibly because of all this research that was going on, somehow the public was aware that there could be such a thing as artificial intelligence, and Hollywood, of course, not to be left behind, had already started, playing with the idea of artificial intelligence. And there were two famous movies, one in 1968, 2001: A Space Odyssey, that introduced an entity, a computer, the famous HAL 9000, which looks like this, that was meant to be an artificial intelligence machine, and it had the sort of the job of managing an entire spacecraft and all the humans who were in that spacecraft. And it was very, very uh, sort of uh, perceptive in its ideas, very far-reaching in its thinking, and in particular, not only is AI seen as an assistant, but it's also seen as an adversary, because in this movie, HAL 9000 ultimately, becomes dangerous. It becomes adversary. It becomes very insecure because once it finds out that its existence might be threatened, it actually starts attacking humans. So pretty fascinating that in 1968, those ideas were already in the movies. And then, of course, it took a rather extreme form in the Terminator in 1984, where it introduced this idea of a neural net-based artificial intelligence called Skynet, an all-powerful system created by Cyberdyne Systems Corporation. It's very interesting that they call it a neural net base. So clearly, neural nets, people were aware of neural nets, and they had come into the public sphere. And this Skynet, of course, is not only is it an AI system, it's supposed to be AI, AGI, ASI, meaning AGI is meaning artificial. It has artificial general intelligence. But not only that, it has artificial superintelligence, which means its intelligence far exceeds that of the humans, right? Artificial general intelligence is usually is a term used for systems whose intelligence matches that of humans, whereas artificial superintelligence means it far surpasses the intelligence of humans. And then, it's also said that it had reached a singularity, which means that the intelligence was so advanced that it was almost alien, that it was something that is completely foreign to humans. And of course, it was completely um, anti or antagonistic towards humans, right? So that's what you see in the Terminator. The Skynet, it's trying to destroy humans, right? Anyway, so this idea of AI as a friend, but also the possibility of AI being a foe, of course, has always been there. And we'll see examples of some of that today. Every now and then there are predictions of doom that you hear about in the news, that famous personalities talk about, that artificial intelligence could destroy humanity and things like that. But it's been sort of going on since 1968. Okay. A key development in the 90s was a major success story of artificial intelligence was AI defeating a human in chess, in particular, not just any human, but the grandmaster, Garry Kasparov, who was the world champion in chess. IBM Deep Blue actually defeated him, twice, I believe. This quote is quite interesting, where Garry Kasparov actually says, I could smell a new kind of intelligence across the table, right? That's quite evocative and, quite vivid, his description. So, of course, since then, there have been many, many examples of computers beating humans, getting really good at playing games. And like I said, game playing has always been a very critical part of artificial intelligence development. Okay, so game playing, theorem proving, problem solving, of course, those are some of the key aspects of artificial intelligence. But in the modern definition of intelligence, there are sort of two views that one could take of AI. One is the the Turing approach to AI, which is mimicking humans or having entities. Those entities are called agents, AI agents, uh, who are who are meant to have intelligence, who are supposed to have intelligence, and they ideally will perform tasks that are human-like, that will demonstrate traits that are human-like, and ideally, of course, because they are machines, they're computers, they could also do them better than humans, right? So mimicking humans is one aspect. Now there's a fundamental problem that you encounter, and that people did encounter, and that they continue to encounter today with AI agents, especially when you look at or when you talk about things like AGI, artificial general intelligence, which is that humans have the ability to perform diverse set of tasks. A human in his or her lifetime will perform many, many tasks, will do many, many different things. And they learn to do those tasks with very few examples. For example, if you take if you take a baby, if you take um, a child will quickly understand the concept of a toy from just a few examples, or they'll understand the concept of a fruit from just a few examples. So if you show a child a banana, and then you show the child an apple, uh, you don't have to show too many examples for it to learn what a banana is, what an apple is, or what a fruit is. On the other hand, for a machine to distinguish between an apple and a banana or something else, you have to show it lots of examples. Also, machines can do narrow tasks. In general, that's why a lot of the focus of artificial intelligence was on problem solving, because that's a more um, you know tractable or more approachable problem, which is doing narrow tasks. So in general, most of the successes of AI have been in um, in performing narrow tasks uh, based on millions of examples, whereas humans, are able to perform lots of diverse tasks, right? So, so of course, the goal is to make AI agents do exactly this, be able to perform diverse tasks with few examples. So that is one goal. But the other goal is, a more utilitarian goal, which is to build AI tools, which is, if machines are good at doing narrow tasks with lots of examples, well, how can we use that to benefit society, right? So it's less about recreating the capabilities that humans have, but um, building systems that benefit humans, but by exhibiting certain characteristics of intelligence, if you will. And again, I still haven't properly defined what that means. Intelligence that benefits humans, right? And so let's do that. Here's sort of a possible definition that could potentially apply, in both aspects, whether you're talking about, intelligent AI agents or AI tools. So, which is this notion of rational agents. So, what is a rational agent? So, first of all, what is an agent? So, in general, in AI, it's very common for people to talk about agents. So, agent is a generic term. It is some kind of an entity. So, you're not saying it's a machine or a digital computer or a human or an animal. You're just saying it's an entity, and this entity has certain capabilities. In particular, one of the capabilities is perception that this entity, it resides in an environment, it has an environment, and it can perceive aspects of this environment, right? So it has, you could say, sensors, like as you see in this diagram, an agent has sensors that can, perceive uh, things from the environment. Those things that it perceives are called percepts, right? So an agent has percepts that it then uses to take actions, right? So an agent also can act. So an agent can perceive and it can act. But of course, that's very general. I mean, you could say, for example, an insect uh, perceives things, it can perceive and it acts. And a lot of the times, what an insect does is it performs reflex actions. Reflex means it has a very narrow set of actions that it can perform, and it performs it almost instantaneously um, without any processing or any intelligence, if you will, right? Okay, or without using rational action. Now that's arguable. I mean, you could say that evolution has created or programmed an insect to perform actions that are crucial for its survival. But for example, an insect, may not do much planning, or it may not be able to deceive an adversary. And if it does deceive an adversary, then it is using some sort of intelligent behavior. But if it is not, if it is simply responding to stimuli and just scurrying away, then it's performing what's called a reflex action. So, I'm sort of leading up to this idea that there's this question mark. You have sensors between perception and action. There is something that goes on. It could be reflexive, which could be like a very fixed set of actions that are there's almost a rule, or there's some processing that happens. Now, what is that processing? So the processing that happens, is dictated by, of course, the percepts, the environment, and the possible actions that are available. But they're all done with the goal of maximizing utility. So that's what distinguishes a rational agent from any old agent, right? You're trying to maximize utility. Now, it's arguable whether an insect simply scurrying off based on, any stimuli is rational or not. We can debate that. Is it maximizing its utility? Maybe it is, maybe it is not. Maybe there's more sophisticated creatures, animals that are more evolved will, do more than just respond to stimuli. They will select actions that maximize utility, right? So there's a notion of utility, the notion of benefit, and there's a way to quantify it. And a rational agent is one that selects actions that maximizes utility. So the Mars rover, for example, is an example of a rational agent. What does it do? It can perceive its environment. It's in an alien environment on Mars, right, on planet Mars. And it's able to kind of, it has cameras that is able to look around and perceive and make sense of it. If it perceives certain types of rock, then it'll act. And the way it acts is it might, pull out or drill. It might drill into that rock, extract some samples, and then store it for analysis. It might perform analysis. Well, all that is example of intelligent behavior, assuming that those are things that are being performed autonomously without somebody issuing commands. That would be definitely example of a intelligent behavior, and that would be considered a rational agent. The utility might be defined in such a way that you have a goal, which is to maybe collect a certain number of samples, or travel a certain distance, things like that, right? Okay, so that's an example. So the key point is that when we're talking about rational agents, if our goal is to build rational agents, there are certain capabilities that are needed, all of which are capabilities that are demonstrated by humans or by living beings, right? And these are capabilities like learning, right? Learning from examples, adapting to new circumstances, and detecting and extrapolating patterns, right? That is one of the attributes. The ability to communicate effectively, the ability to communicate in a natural language, right? So you could communicate through a special purpose set of instructions, through special commands, through special language, like a programming language, or you could communicate through natural language. So you do expect an intelligent entity to be able to communicate in natural language. It's a critical aspect of intelligence. The ability to perceive, in particular computer vision or vision, being able to look at images or videos and be able to perceive them, to be able to make sense of them, right? So computer vision. And then being physically embodied, meaning the ability to manipulate objects and move about, right? These are all attributes that you would that are indicative of intelligence, and that typically would be expected of a rational agent. If you're talking about a rational agent like a robot or a self-driving car, right? Mars rover, these are all things that exhibit these types of attributes. Now, of course, you might have a system that only focuses on one of these attributes, right? And that could be pretty useful in itself. But when all of these things are working together, you have this powerful entity called a rational agent, right? So let's look at examples of these different attributes, things that are actually exhibited by various entities today, right? By various systems today. So natural language processing, you have speech technologies that are, like Siri, for example, or Amazon's Alexa. They are all exhibit speech recognition, text-to-speech synthesis, dialogue systems, right? And then you have language processing technologies like question answering, ChatGPT. It's a great example. Machine translation, Google Translate. Here's a kind of example of translation. This is an article from Le Monde. It's in French. And then, I pull it up on Firefox, and then I asked it to translate it into English, and it does that immediately. So machine translation is, again, a key example of natural language processing, web search, semantic search, text classification. Those are all examples of natural language processing, right? And then computer vision. What are some of the tasks involved in computer vision? Image classification is one of them. Being able to look at an image and literally classify that entire image. Is this the image of a cat or a dog? Is this an image of a dense crowd or something else? Like literally being able to assign a label to an entire image. That's called image classification. Object detection, which is the ability to identify objects inside an image and literally draw a bounding box. So, for example, here The system is able to detect that there is an object here, and then is able to draw a bounding box around it, and then it's able to then determine what type of an object it is, that it's a dog, and here's another dog, here's another dog. And here it's able to draw a bounding box and identify that it's a plane, right? And then there are things like semantic segmentation and instance segmentation, where literally it's able to classify a pixel. It's literally able to look at a pixel and say, what type of an object does that pixel belong to? Or, again, identify subsets of that image and classify them, right? So those are all computer vision tasks, right? Robotics, of course, these days there's a lot of progress that has been made in robotics. Of course, fully self-driving cars. Those are great examples of robots. Mars rover is another example of a robot, right? Okay, so these are, some aspects of artificial intelligence. The agent concept, the idea of a rational agent, and having these key capabilities. In the next video, I will talk about the underlying technologies that enable these capabilities and some of the progress that has been made in the 21st century in achieving those capabilities. Okay, until then, thank you very much. See you next time.